Gene from Mavestar Observatory. What we've tried to do today, and I'm going to go through this shortly with you, is just try and get an idea of how much cosmic radiation is entering the entire Earth. And I know it's not fair to do the way I've done it, but I don't know any other way of getting an idea unless we do that. So what I've done is I've worked out the surface area of the detector, which is 5 centimetres squared. I've worked out the surface area of the Earth, which is 510 trillion square metres. So I know we're going to go into the powers of 10 because it's just easier to write that than it is lots of zeros. So, 510 trillion square metres is 10 to the power of the 12. And that's just an indication of how many zeros are afterwards. So, when we're looking at numbers like this, 4 to the power of 16, what that accounts for is the amount of Muon detectors with a surface area of detection over the entire Earth. So what we would have to have in order to get that number of the Earth's surface area covered with these muons is 4 to the power of 16. And then obviously once we understand that number, which is the surface area of our muon counts, we can then work out how many muon counts on average over, we've got 3 times there, which I've taken. Don't worry, I'm going to get the camera a bit closer so you can see these numbers and we'll go through this. But we took 4 different readings with this Muon detector, and at one point over an hour we got 1,869, which I thought was quite a lot. The LED on the front of this and the count rate was going up very quick, and that was only in an hour's time. But it's not always the same, and I think I know what the answer for that is, and we'll get into that in a minute. But here we had a reading that was done over 4.5 hours, and we've only got 243 counts of muons. Again, over 1.5 hours, 296 counts, and then over 2 hours we got 200. These have been taken, these readings, at different times. I haven't gone 6 o'clock and then 6 o'clock the next morning and 6 o'clock the morning after. They've been done at random times. So I know we've only got 4 readings yet, but we've got 4 different answers. And I think the reason for that is because there's a lot going on and a lot we have to take into account. First of all, the Earth is rotating at 1,000 miles an hour. So at one particular point in time, this isn't going to be pointing or receiving muons from that same source, perhaps where we was getting a higher reading over an hour. An hour later, we won't be in that same region where those muons are coming into our atmosphere as a result of collisions in the upper atmosphere, as a result of cosmic radiation striking, the molecules within our atmosphere. Another reason is we've got to also factor in is the Earth travels around the Sun at around about 70,000 miles an hour. So again, the location changes, and it changes all the time. So even if we've done 365 days of counts, and we counted 24 hours of the day, so we knew where it was rotating, we still wouldn't come back to that same point in our galaxy, because even our Sun, what we orbit around, migrates as well. So there's a lot going on, and it's always going to change, and never are we going to get 2 days the same. But what we can look at, I know it's a bit exotic to do this, because what we've said is, okay, if we covered the entire surface area with these muon detectors, and they all give us the same amount of counts over that period of time, we could then use this equation to find out how many muons there would be. If we just quickly look at how many we got as a result of that, we got 7.476 to the power of 20. That's a huge number when you consider 10 to the power of 12 is 1 trillion. So, 12 zeros after that, after just that number. And when we get, that number times 4 to the power of 16, we end up with that big, huge number to the power of 20. That is trillions and trillions of muons over that period of time, over an hour, if we did it like that. I know it is a bit unfair because, I could have one of these in China and it won't read the same as what we're getting here in the UK. And that's just, the advantage of wherever the one is in China at that particular point in the day or time of the day where the muons are coming from that particular point of the galaxy or from other galaxies. We just don't know where these are coming from, and that's why, you know, so many millions of pounds are being spent now on cosmic ray detection, because what they're trying to work out is where the main sources are for these. But you know, they come from all over. They come from our sun, they come from collisions, from other parts of the universe. We do know that muons can only exist for about 2 milliseconds. That's their half-life, and I've been through this before. You know, we shouldn't even have them on the surface of the Earth, but that's to do with time relativity. Time is relevant just to the muon at that particular thing, at that particular point in time, because you know, in order for it to reach the surface, it'd have to travel 10 kilometres to the surface, and by then the 2 milliseconds of its lifespan would have exceeded that. Well, the reason it doesn't for the muon is because it's travelling at almost the speed of light itself. So that's how it avoids it. And if you remember, as someone did mention correctly in the comments section the other day on the video, that, you know, there have been experiments done to prove this. We've put 2 atomic clocks together, put them on planes. When we've put one on a plane, one on the ground, when they've come back, one has slightly been advanced than the other. So we know that speed does affect time, even in the slow speeds that planes travel. There's another one where 2 twins are on board 2 spaceships, and one travels one direction for a period of time, one travels another direction for a period of time, and when they come back, one is nearly a year older. It's just a theoretical you know, way of getting your head around it. But yeah, time travel is possible, and our muons are, you know, are actually proving that. So it does prove relativity with regards to the muon at least. So let's get into how I come up with these figures. So what we've got to bear in mind is that what we can do only with these muon detectors is detect the rate over its surface area. We can project the surface area over the Earth, and we can say that, you know, if it was a perfect shower evenly over the Earth, we would have this number. But I will say this, we're probably not far off the amount of muons that we're getting here with this. So it's a good reference point at least. But what we can detect with these is if over this square area, if this muon detector's not moved, we can get an average of whether muons are on the increase, and if they are, and they should be, because we're in a grand solar minimum, that means that the heliosphere of our Earth, of our solar system, is shrunk and allowing more cosmic radiation in. And on top of this, we've got another rare anomaly taking place with our Earth, and that is the magnetic poles of this Earth are going into a reversal, or at least, you know, it might be an excursion. I feel like I always have to say now, as a disclaimer, an excursion, because people do talk about magnetic excursions, but the difference between a reversal, a completed reversal, is that it did reverse and held its magnetism at that point. So north would have been on the south and south would have been on the north, whereas an excursion, the poles would turn but then go back. That would be called an excursion, and as you know through the records, if we go back, there has been many excursions, but not so many of the rarer event, which is the reversal. So there you go. So as a result of a reversal and a grand solar minimum, we're getting more and more cosmic radiation inbound. And with these, we can detect, at least over this surface area, how much is increasing, and we can take an average over the year, and that's all we can do. And it'll be a good average. It'll be, you know, a good average for the fact that we are actually counting muons. But the only downfall about this is, as I've said at the beginning of this video, you know, we're spinning round, the muon detectors pointing at different parts of our solar system and elsewhere if we go beyond our solar system. And not only that, we are travelling around the sun. So just bear that in mind. But I will say this, I think that that's a lot in any case. Over 1 hour I recorded 1,869 counts of muons over that small surface area. So it just makes you wonder how many is actually travelling through our body, through the buildings. There's no protection. I got a piece of lead over this detector this morning, and the detector was still going off. The lead did not block the muons, and you wouldn't expect it to either, because they're a lot smaller than the lead particles. But nevertheless, you know, we've got, at some times of the day and night, a hell of a lot of muons at this moment going through us. And they can be carcinogenic, they can cause cancer if you're unlucky, and they do strike part of that deoxyribonucleic acid in your cells, the DNA, and you know, they can create mutations of those chains of DNA. If that happens, it's simply known in a scientific field as cancer. And you know, if you get one mutate and not obey the rules of which it was supposed to, it will continue to grow out of control, and you end up with lumps and other forms of cancers. And as you know, there are plenty of different cells in your body, so you can get many different types of cancer. And you know, if we're having a massive increase of cosmic radiation, then you know, those risks increase a lot. So, you know, at some points we have what seems relatively low readings. I mean, over 4.5 hours we only had 243 counts, but just over this 1 hour we had 1,869. The only difference was the difference at time and probably the position of the detector with regards to where it was pointing out into space, or where the cosmic radiations were coming from. So that's what we've got to bear in mind. Let's have a look how we got to these figures then. So, like I said, I had to work out the surface area in metres, and as you can see, it's 510 trillion square metres. Right, so if we work out then the surface area of the Muon detector, surface detecting area, it's 5 centimetres squared. So 400 of these muons would fit in 1 square metre, and to get the average of muons we need to multiply the surface area of the Earth by 400, because there's 400 muon detector surface areas in 1 square metre, and we're working now on the area of the surface of the Earth in square metres, and that's why these numbers are big. So the area in square metres is, as you can see, 10 to the power of 12, which is the same as 510 trillion square metres. So we've got that times by 400, because we're using the surface area of our detector, which is 5 centimetres squared. So there's 400 of them, so whatever number this is, it's got to be then times by 400, and then that gives us in powers of 10, obviously 4 to the power of 16 times the muon counts over time. So the numbers that we need to concentrate on are no longer these two here, just this one, which is 4 to the power of 16. And over 1 hour we had 1,869 counts of muons. We times that by 4 to the power of 16, which is the surface area in muon detectors, and we get this number here, 7.476 to the power of 20. Oh my god, can you believe the size of that number, guys? It's absolutely humongous. We're talking trillions and trillions of muons over the entire surface area of the Earth if we scaled it up to that over 1 hour. So over 4.5 hours we got slightly lower reading this time. It was 243 times 4 to the power of 16. We get 9.72 to the power of 18. Still a huge number of muons over the entire surface area. If we're getting average showers of muons over the entire surface area, and if we've got muon detectors over the surface area, covered every little square inch of it, this is the numbers that we would have. Again, over 1.5 hours we got 296 times that by the surface area, and we end up with 1.184 to the power of 19 muons. And then again at the last one, 2 hours, we got 200 muon strikes, times that by 4 to the power of 16, we end up with 8 to the power of 18 muons. It's a huge number. All these numbers are massive. But it's just to give you a rough idea. If we were living in perfect circumstances where we got the same amount of muons as what we did over just the one muon detector that we've got here over the whole entire surface of the Earth, and if it was evenly raining down on the surface area of the Earth equally as well, we would have that. But what we've got to remember is we travel round the sun, the Earth rotates, and at any given time from anywhere in our universe these cosmic rays can come from. And like I say, the reason why there's so much money being spent now is because they're trying to find out where the main sources of these cosmic rays come from, and learn more about it. So I just thought I'd include that for you guys. So tomorrow I'm going to whip out the SD card out the TriMag system, and we're going to do a location of the magnetic North Pole. We'll also look at what data we've collected since it was all reactivated. We'll also have a look at the magnetosphere strength sensor, see what we're getting there. And we're not we're about, I don't know, about 8 days away from the end of the month, are we? Something like that. So we might start getting some more data as well come over the next 8 days from those different locations. But guys, we would never have got to this if we'd never built that if we'd never built our Muon detector. We wouldn't have a vague idea, even if there was perfect circumstances, how much radiation would be inbound with regards to these muons. And the reason why we have is because there's been a joint effort with you guys supporting us at the Mavestar Observatory, which has enabled us not only to build these recent Muon detectors, but also the magnetometers that we've got at different locations already around the world. And remember, that's what we want to do with these Muon detectors. And we can put one in either South Africa or Brazil, and we can get an idea of that lowest intensity region of our Earth where the magnetic field is at its weakest. We can also put one in one of the largest intensity regions in Australia, and we can also put them in different locations. It gives us a lot of understanding of what we're up against. But more importantly, from now on we're going to start collecting 24-hour and 365-day readings over the year, so we'll know how much radiation is at the location of the detector, and that is better than what we're getting right now from a lot of other organisations which are keeping quiet about this. Remember, it is expected to increase cosmic radiation during a time of grand solar minimum, and it's also expected to increase in a time where the Earth goes through this rare event, a magnetic reversal. So that's why it is important, guys, that we keep doing what we're doing. And the only way we can do that is if we raise some funds to keep the equipment running, and keep building the equipment and keep sending it out there and getting the data back. That's the only way we can do it. So this effort that I know a small amount of you are doing just needs to be sustained, and we can continue doing what we do here at the Mavestar Observatory for you guys. So with that, I've left it to the end. I know a lot of you will be pleased about this. I'm only going to mention the link once. I'm going to say thank you to all the people that have supported us so far. We've still got a lot of work to do. And if you want to help, guys, there's a link down there. And that's the main thing, that we do get help from some of you guys out there. So have a great weekend, and I'll catch up with you perhaps over the weekend. We'll see. Like I said, I'll pull the SD card out of the TriMag tomorrow and get that data for you as well. So have a great evening, and I'll catch up with you tomorrow. Links down there if you want to support. As always, bye for now.